Suppose you woke up on a desert island next to a sign that looks like this. You've probably seen these signs before at like tourist traps and stuff. You're this many miles away from Mumbai, you're this many miles away from the Philippines, and this many miles away from Toronto, and so on. Could you figure out where you are based on these locations and distances? So let's use Mathematica's Geodesy functionality to figure it out. Now the basic idea here is if you knew you were 1,200 miles from New York and 1,800 from San Francisco, well, you could draw around New York City, you could draw a 1,200 mile radius circle, and you would know that you'd have to be somewhere on this circle. Similarly, you would draw an 1,800 mile radius circle around San Francisco, and you know you'd have to be somewhere on this circle. So therefore, you have to be either here or here. So if you had maybe a third circle, geocircle, with maybe Houston, centered at Houston, and maybe you're 229 miles from Houston. That would add this third circle down here, and therefore all three of them are touching at this little point here. Let's zoom in at this little point here, and you can see that you would be therefore somewhere between Alexandria and Lafayette at this point here in Louisiana. Okay, so let's figure it out for this sign here, which has a bunch of cities, and hopefully all their circles will intersect at a single point. But we'll see that that may not actually be the case. So here's a list of pairs. Each pair is the name of the city as just a string and the number of miles. Now in order to use Mathematica's geodesy functions effectively, we'll need to, first of all, tell Mathematica that this is not just some random integer. This has units of miles. That's what this does here. We're going to tell this is a quantity, it's this number and this many miles. And then we need to tell Mathematica this is not just some random string. I want you to interpret this as like an entity that has a bunch of like properties, and one of those properties is going to be the coordinates, like the latitude and longitude. So just as an example, if you haven't seen the Wolfram knowledge base stuff before, it's pretty cool. It's something that not a lot of other programming languages have built in. Use this function semantic interpretation, and you give it just a string, and it will interpret that string as an entity in the Wolfram knowledge base and give it this little orange outline here. And if I ask it, what sort of properties, what do you know about New York City? It will tell you, gosh, I know a lot of stuff about New York City. For instance, here I know the median home sale price of houses in New York City, and I can just pop that in here, and it's about $500,000. I can also ask it, let's see, maybe you saw down there was also coordinates. So here's the latitude and longitude of New York City, and that's what is going to turn out to be useful here when you use entities in the Wolfram knowledge base for this kind of stuff. Okay, so that's a quick whirlwind tour for how the Wolfram knowledge base works with its entities. So what we're going to do is we're going to make a table, just a list of geocircles. These are graphics primitives used for geodesy. And the first element, I'll just look at the help for geocircle. The first element has to be some sort of location, and the second element has to be some sort of radius. And if you look at the details here, it says, well, the location can be specified as a latitude and longitude or as a geographical entity. So that's why we're using the semantic interpretation. And the radius can be used, you can specify as some sort of quantity up here. Okay, so we will give it the location as this semantic interpretation, and we'll give it the quantity in terms of miles. Okay, so if we do this, we will get a bunch of geocircles, and it takes a second for it to go out and interpret all these strings. I think it has to talk to the Wolfram servers. So here we have geocircles with these locations, centered at this location with this radius. And so if we call geographics on this, we get all these circles. Some of these circles are distorted due to the projection of the sphere of the Earth onto this screen. And so if we then ask for some sort of dynamic geographics, we'll get this little dynamic map, and we can sort of go around and click, and hopefully all these circles should intersect at a single point. You can see that they're a little bit off though. It looks like they're kind of converging on the Cayman Islands, but they don't all meet at one point, not as nice and neatly as it did up here, as they all did here. So let's see how bad it is. In addition to the circles, I'll also add a geodisk centered at the Cayman Islands with radius of 100 miles, and we'll see how close we can get with our circles currently. And you can see that, gosh, some of them are intersecting way outside, like hundreds and hundreds of miles away. Here's more than 100 miles. And even inside, they're not that close. So there's no way you could figure out how to get, how you could figure out, well, precisely where you are. I guess you could say I'm on the Cayman Islands. Let's see if we can do better. Let's see if we could fix this sign. Okay, And I happen to know, because I was there when I took the picture, that it's at the Cracked Conch, which is some restaurant on the northwest side of the Grand Cayman Islands. So here's the Cayman Islands, and there's the Cracked Conch on this side here. Okay, so let's pull out from our list of circles. These are the circles that don't quite all converge. The list of places and the distances that are sort of bad distances because they don't quite get us where we want to go. Let's make some better distances. So we'll make a table of distances where each distance goes from the Cracked Conch to some place, one of the places in this list here. And we'll use this distance function center because by default, if you don't have this, geodistance will return the sort of the minimum distance, the distance from the Cracked Conch to any point in this, say in Latvia. We want to go from the center of Latvia, so we'll use this option, the distance function option here. Okay, so here are all of the distances to all those from the Cracked Conch to all of these different places. And then we'll sort of wrap this up with our places to get these better pairs. So before the pairs were just strings and then the miles, but now they're the entities and some better distances. And we'll wrap geocircles around all those pairs and then throw it over the fence to dynamic geographics. So we'll plot our circles. We'll put a little marker at the Cracked Conch just to sort of verify that they're all converging where we want. And we'll also draw a 1 mile radius circle, disk around the Cracked Conch just to sort of get a sense of scale. So if you zoom in here, you can see that, let's see, I'll get a similar zoom level to before with sort of this island off on the side here. You can see that all these circles really do a nice job of converging where the marker is. And contrast that with here. Well, I'll get to a similar zoom level, and you can see that, gosh, they're not all converging very well. So this is a big improvement. However, if you zoom in, if you say, well, could I actually find the specific restaurant, could I get precisely on top of it? Well, the answer is no. You're still, even though this is a 1 mile radius thing, you could be spotted by an airplane or something. That would be good. You could be rescued, but you couldn't get to the restaurant. Exactly. You might wonder, why are these circles not all intersecting at a single point? I constructed them specifically so that they would be the precise distance, and yet they're not all intersecting. So I was puzzled by this, and I asked my friends at the Mathematica Stack Exchange website, and they pointed out that, hey, when you're drawing a circle that is like as big as the Earth, how the map is drawn might actually, it's not going to compute an infinite number of points on this circle to draw them. There might actually be some sampling problems with this circle, and that make it so that it doesn't all line up, so that they aren't exactly concentric. So one way you can sort of hack around this is if you only draw circular arcs instead of the whole circle, how about just draw the arc of the circle that goes through the part of the Cayman Islands that you care about. So we won't draw the whole circle around Jamaica, for instance. We'll just draw a tiny circular arc, maybe a couple of degrees of the arc around here. We'll just draw this part, not the whole circle. And so here's how to do that. The arc length will be maybe 1 angular degree, and we'll update, instead of drawing, we'll update both our original circles and also our better circles. These are our better circles that we computed from before. So we're going to make some arcs and some better arcs based on the list of circles and the list of better circles. And the way that that's going to work is we will just append, because if you look at how the circles work, the geocircles work, you can, whoopsie daisy, there we go. In addition to the location and the radius, you can give it a bearing. This is just a sector of a circle from a couple of bearings, alpha 1 and alpha 2. Okay, so in addition to, we will just append to each circle in our list of circles a bearing, two bearings. And so this will be our our -1 and +1 degrees, but we also, if we just leave it at -1 and +1, that'll just give us this bearing here, -1 and +1 from true north. We need to offset that by the angle from Jamaica, for instance, to the Cayman Islands. So we need to add an angle to that -1 and +1 in order to shift it around to the correct arc. So that's what this geodirection is. Okay, so that's how that works. So whereas in the old days we had a circle that was, centered at Mumbai and had this radius, which was on the sign, now from that we have an arc that has the same center, the same radius, but now we're only going to be plotting the circular arc between these two bearings as measured from true north. Similarly, now we had these better circles that we computed from the actual distances. So instead of 9,271 miles, it's this slightly different mileage. And these better arcs, so the better arc associated with that has just appended to it these bearings here that specify what part of the circle. Okay, so let's see if I mean, you could look at this and say, oh my gosh, Justin, well, like, here's the reason that this is so bad. Like, our sign is actually correct. It's Mathematica that is drawing it poorly. Let's see whether that's actually the case, because we'll use our circular arcs and see if it works any better. If we draw our circles and then maybe a marker at the cracked conch, here's maybe a 1 mile radius around the cracked conch, and then in thick red lines we'll draw our arcs, and we'll see if there's any difference. So we'll zoom in here, and you can see that the arcs, the 1 degree arcs, are clustered around the Cayman Islands. That's good. But they're so far off. There's hardly any difference. The sign is really at fault here. The distances are so off that there's hardly any difference between the poorly rendered gigantic circle and the much more precise circular arc here. So you can see that even though, yeah, truly there is a rendering difference between the giant circle and the circular arc associated with it, that wouldn't have changed our guess of where we are in on the island. It still would need to be improved. And if we run it for our improved circles and the improved arcs that we derived from them, you can see that they all converge very precisely at the actual restaurant. Here you can see that the circles and the arcs are beginning to diverge, and that I'll zoom in all the way we can possibly zoom in. You can see that I've got this 20-foot radius circle around the cracked conch, and all of the arcs intersect it beautifully. And so that's a great improvement. Okay, so we feel confident that those truly are the distances that should be on the sign. So whereas before these distances were like this, we feel that they really should be these numbers here. And what's the difference? How far off are they? Well, most of the time they're pretty close, but there's sometimes where it actually is more like 20 or 60 miles off. And so that's something that we could maybe I'll email the cracked conch, and they can fix this up. Okay, great. Thanks for watching.